All right, class, let me make another video solution from Chapter 5, as many of you are studying and getting ready for the exam, and some of you, looks like, are actually taking the exam at this moment. Now, that being said, let's work on this one. I'll read the question first. It says, calculate the maximum acceleration of a car heading up a 4-degree slope under the following road conditions. Assume that only half of the weight of the car is supported by the two drive wheels and that the coefficient of static and friction is involved. That is, the tires are not allowed to slip during the acceleration. All right, so if I kind of draw a small angled hill, something like this, so this is, actually that's a more than 4 degrees, but give me some room to work with. There's a 4-degree hill. And if I put a car on it, this is that first step that I said, all right, get a good physical picture of what's going on, and then we can do a free body diagram. And when I say a good physical picture, this problem is kind of hard in itself, but there are two other aspects about this problem that I think it makes it very hard. So I'm going to address this first one here, and that is getting a good understanding of this really involves getting a good understanding of what's going on between the tires and the road. Because if I were to forget about the tires for a moment and just put a block up here and say that the block is moving to the right, you would have no problem telling me that the friction is to the left, opposite of the direction it's moving. Now, I'm going to change that. It's opposite to the direction it's sliding. And here's why that's important. When you have a tire, and so I'm going to do this twice. And so let's put a tire on the road, okay. And let's just say the tire is moving to the right, okay. Because the tires on the drive wheel anyways are able to spin or try to spin faster than the car is moving, or you can brake with them, two interesting things can happen, although really they're one and the same, but the direction is different, and that's what I want to point out. Let's start with, I think, the easier case. So let's say you have a tire that's rolling, and you apply the brakes. Now, if you massively applied the brakes, it would lock up the tire, and you would slide, and therefore you would say the friction is to the left, it's opposite of the sliding. And really, that's no different than the block I just said. However, here's where it gets interesting. What if instead of applying the brakes, you're applying throttle, you're applying gas? And let's go to the extreme case. In the extreme case, the tire would spin, and right here on the surface, this bottom tire would be moving in a leftward direction as it slides along the road. And so opposite of sliding is actually, surprisingly, to the right. And so a tire can have friction either opposite the direction it's moving or actually in the same direction that it's moving. I would say both of these are the same, that the friction is always opposite of the slide. It's just that when you are applying gas or the throttle to these rear wheels, they want to go actually spin faster than the road. So the sliding, or if you don't have enough power to make your tires actually spin, at least what it wants to do is slide to the left. The movement of the tire is to the left because you're spinning the tires or trying to spin them faster than you're actually moving. And that ends up with a result that might make this problem kind of confusing, because what I'm going to do is actually put the force of friction in the direction that the car is actually moving. And I needed to say that first, because that can get overlooked. So when I do a free body diagram for this problem, and I just make kind of a little dot here for the car, and I say, okay, now what forces are on this car? I'm going to say, well, clearly the weight of it, so there's mg, and then everything touching it. And since we're on an incline, the normal force is going to be tilted a little bit. And this is the part that, without a deeper discussion about the tires and the slipping, you may be going, what? What do you mean the friction is up the hill? I thought friction was opposite to the motion. And I'm going to say, no. The friction is an opposite of the sliding. And so a tire under power wants to actually slide, like I said, in this picture to the left, and when it's moving to the right, therefore the friction is to the right, in the direction it's actually moving. So this would be the direction for the friction when we are applying power to the car. As opposed to down the hill, this way, I better not write it on here, I'll just put a little dot. But that would be the direction down the hill if I was applying the brakes. And that would be this scenario. But since it says, calculate the maximum acceleration of the car as it is heading up. So they want to know what's the acceleration as it's heading up. So you're giving it as much throttle as you can before the wheels spin. And so, depending on the power of your engine, they may never spin, but some cars, have enough power they can spin, or the road conditions are either wet or icy, so they could spin. So you don't want to give it full throttle, just enough to get the maximum acceleration. All right. Well, hopefully if it's icy, you're not trying to get maximum anything, because that's not good. You're at the risk of causing an accident, hurting yourself and maybe others. Now, that being said, this is my free body diagram. All right, so let me call this page 1, because my comment is always these first 2 steps: good physical picture of what's going on, and then a good free body diagram. And like I said, good physical picture is important to get that force. All right, now we can get to step 2 that I keep talking about, and that is to write out the equations. And what I mean by that is you add up all the forces in the x direction and set it equal to mass times acceleration in the x direction. And you also add up all the forces in the y direction and set that equal to mass times acceleration in the y direction. And this is this phrase that I keep saying. Physics is not about learning and memorizing a bunch of principles. The principles we have are fundamental, and there are few of them, but they are powerful. And so there's just a few powerful fundamental concepts that explain a universe of phenomenon. And that's why this statement is true for chapters 4, for chapter 5, and chapter 6. And then a lot of deductive reasoning. So not a lot of memorization. In fact, I'm looking at how the author did the solution. And they didn't go through this. I mean, they the first thing they write down is a big equation that kind of puts all this together, and it's kind of disappointing looking at the author's solution. It's like, whoa. I mean, students are going to ask right away why the friction is up the hill, and there's no discussion about that. So I thought I would add to it. Also, all this math I'm about to do. And like I said, there's 2 tricky things here. And that first one was the friction up the hill. The second one is still to come. But even without those 2 tricky things, this is kind of hard. So let's write these out. Now, before we can write them out, we also have to choose a grid. And I told you guys, I'm going to say it again, that any grid would work. but some are really hard and some make it so much easier. And the trick I want to tell you is set up one of your axes, usually I just do the x, in the direction of the acceleration, because what will end up happening means the other acceleration would be 0. And it's nice to have equations that have zeros in them. They're easier to solve, easier to substitute in. It also means that if the ultimate question is to find the acceleration, you only have to do it in the x direction. If you had an x acceleration and a y acceleration, then at the end of the problem, you have to do the Pythagorean theorem, which would be x, squared plus the acceleration in the y squared, and then the square root of that. And that's an extra step and can be a really hard step if there's an angle involved, because then you have sines and cosines and you have them squared, and then you have to do some trig identities. So all of that is the same thing I was saying in lecture. I said it today for chapter 6, and then I also said it when we were here in chapter 5, that set up the grid. And so in this case, I'm going to set up a grid, put it in red, so that x is up the hill. It makes y perpendicular to the hill. And now I'll write out the equations according to this grid. And so it's not the traditional grid. The traditional grid probably makes you feel comfortable because it's tradition, but it'll be mathematically hard. And this is already a hard problem, even with this grid. Then you add in the friction, and then you add in that second one, that thing that has to do with the fact that only 2 wheels have drive power and the other 2 just free will. So let me use this grid. All right, so keeping in mind I'm using this grid, I'll even maybe keep it at the top of the video here and go on to page 2. Let me write out the equations using this grid. And so to illustrate that, I am going to add up the x and y of each force. Let me start with the first force called the normal. And when I look at the normal, it's all in the y, which means none in the x. So right here at the x, I'll put 0, and for the y, I'll put n. And of course, you don't really need to put a 0 in an equation, but I'm doing this for your education, saying I want you to realize that I am doing every force and the x and y for every force. So there are 3 forces, and I'm going to do 3 x and y. And so this is the first force, all y, no x. I can kind of do the same thing with the friction here. Friction is all x, no y. So I would go plus f and plus 0. So there would be the second force, the x and the y component of the second one. Now, the gravitational force might be the hardest one. So I'm going to point out that this here is 4 degrees. That's because I tilted my axis up 4 degrees. So if the x-axis tilts up 4 degrees, this, which was down the y-axis, would shift over 4 degrees. And if I, maybe in a green color, looked at the components, I would see I'll call it the negative part of shifting my axis. That is, this weight, which used to be only in the y direction, now has a little bit in the y and a little bit in the x. And if you look, it would be negative y and negative x. So both the x and y component, first of all, I have both an x and y component. They're not a 0, and they're both negative. So back here in my equations, I'm going to put minus and minus. So there is an x component and a y component. Now, the x component would be this over here. It would be opposite of the 4 degrees. And remember, it's the trig function that's a sine that gives you the opposite. Remember, sine of theta is the opposite over the hypotenuse. So if you take hypotenuse and sine theta, you get opposite, okay? So I'm going to say to get the x component, I would take the hypotenuse, that's the mg, and then multiply it by sine of theta, which in my case I know theta is 4 degrees. I'll just leave it as a symbol for the moment. We'll put that in later. Now, using the same logic here and pointing out that cosine function is the adjacent over the hypotenuse, I would have h times cosine theta is the adjacent. Okay, so I'm going to then write this as hypotenuse, mg, and then the adjacent is cosine of theta. So there you can see it, 1, 2, 3. The x component of all three, 1, 2, 3. The y component of all three. And that has to equal to ma in the x direction, and this has to equal to ma in the y direction. Now we can take a big advantage of why I tilted my axis, because what's the acceleration in the y direction? 0. And the x direction? All of it. And so I'll just call it a. I won't even put a sub x anymore. This is all the acceleration. So that's what we're after. Remember, the question says calculate the maximum acceleration. Now, maybe I'll focus my attention here on the y-axis. Since this equals 0, I can then move the negative to the other side and say that the normal force is mg cosine theta. And we've seen that a couple times for something on a hill, going up and down the hill. So you might remember me doing it in class, and I know the book also did it a few times. All right. Now, maybe I'll work this one out. First, I'll try to squeeze in the MA and then just kind of write it without the 0. So not a big step yet. But it gives me the chance to talk about the force of friction. Because remember, the question says find the maximum acceleration. And it says without the tires slipping. So this would be static friction. And let me remind you that static friction is an inequality. It doesn't equal a number. It can be some smaller values up to a maximum, where the maximum is the coefficient of friction times the normal. However, let me use the equal sign as I solve this, because the problem is saying maximum acceleration. That comes when you have the maximum friction. The maximum friction is this value. Kinetic friction is always less than that. So that'd be if the tires were spinning or sliding in some way. And so even though technically the static friction is an inequality, I'm going to use the equality because of the way they asked the question. So this is mu s, and I'll put n in here, but I'm going to put n in quotes for just a second. And I'll come back to that. Let me finish writing out the equation. You see, the reason I put this in quotes is because this would be the normal force where the drive wheels are. Remember, the friction only comes from the drive wheels. But remember, this is the total normal force of the whole car. Remember, when I did this free body diagram, I did the whole car. And so the second thing I was kind of warning you about that would make this problem hard is I'm going to say that the normal force on the drive wheels only are 1/2 of the total normal force. That's why they said there, be careful, because only 2 of the wheels are pushing the car. And so I get a friction, but only from 2 of the wheels out of the 4. So the total normal force is on all 4 tires. Half of that would be on the 2 tires that have drive to them, and that's why I put the quote here, because I would want the normal force where there's friction, and where there's friction is only on the drive wheels, which is only 2 of the 4, and hence the 1/2. So 1/2 of the whole normal, that's this up here, I can then put this in, mu naught times 1/2, and then over here I'll go mg cosine theta minus mg sine theta equals ma. And believe it or not, your author, well, he has a line right before this, but it's only one. This is the second line in his solution. And that's a big step. But I guess I kind of understand why. He's saying, look, we've done normal forces before, and we get mg cosine theta. So he just plops that in there and then says take 1/2. And he also says we've done the force of gravity down a hill and got mg sine theta. So he just plops that in. So this is up the hill, this is down the hill, and equal to acceleration, and begins from there. But I'm not sure that makes a good solution. I mean, I'm 21 minutes into the solution, and it took me that long to actually get here. Of course, I started from scratch, and I didn't use the stuff that we derived earlier. I actually worked it out. Okay, now if you'll notice, there's an m in each term. So if I divide everything by m, they would cancel off. And that's good, because I will tell you, I was getting a little nervous not knowing a mass, and they said maximum acceleration, and I was seeing all these m's in the equation, and I was like, ooh, how's this going to work? But glad to see this step here. All right, so now I can finally answer A. The acceleration is equal to what? And so in A, it says when you're on dry concrete. So I'm going to open up my book here, and I'm going to go to the little chart that says mu s equals 1.0 for rubber on dry concrete. And I'm going to use that and then calculate this number. So this is a 1 times a 1/2 times a 9.8 times a cosine of 4 degrees minus 9.8 sine 4 degrees. And I get 4.20 meters per second squared. And so that would be the maximum. Again, if you tried to do a greater acceleration than that, you would need a greater force. And to do that, you need a larger coefficient of friction. Otherwise, the tires are going to just spin. So assuming you have enough power from your engine, they'll just spin. You can't do better than that. Now, B says go ahead and do the same thing on wet concrete. So now let's say we're driving up the hill in the rain. Well, that reduces the most or the maximum friction we could get, which is why that's going to reduce your maximum acceleration. So I typed all these in, and if it'll be okay, then I'll just use the cheat part on my calculator and replay the last entry. Because the only thing that's going to change is right here at the beginning where I typed a 1. Now I'm going to type a 0.7. And I better change that to insert mode to type in a 0.7. Then I'll go back to delete mode, or just delete it. All right, so there's the 0.7. In fact, I better just kind of check. So 0.7 right here times 0.5 times 9.8 times cosine of 4 minus 9.8 sine of 4, then equals 2.74. So the maximum acceleration before my tires slip is something quite a bit less. Oh, and I should put meters per second squared. And then finally, C, let me go back to the question. I think it said something about, try this same thing when there's ice on the road. Okay. Well, when there's ice on the road, they're saying that the coefficient is 0.1. So again, I'm going to use the little calculator cheats and go back here, and instead of having a 0.7, I'm going to have a 0.1, and hopefully everything else is still the same. And this one's interesting because it comes out to be negative 0.195 meters per second squared equals 2a, which, of course, reading the math tells me that this force pulling it down the hill, which is a component of gravity, is actually stronger than the most I can get from the tires going up. And so during this icy conditions, I can't get up the hill. It's no way. If I'm even partly on the hill, now I'm going to go roll backwards. And roll is probably the wrong word. Slide backwards. The force of gravity is more than what I can get from the tires. Obviously, a dangerous situation. There's just no way you're getting up the hill. Your acceleration is negative. And of course, probably now your tires are slipping. And so we would have to change this now to a kinetic friction, which would be even lower, which means you're going to go down the hill even more. So, but that's not needed for this problem. All right. I'll call it quits for this one, but real hard one. Harder than would be on a test. This little subtlety of this 1/2. This little friction in the direction it's going. Now that we did it, I guess that wouldn't be so bad on the test. Multiple parts would be too much, but just a part A would be good, because this is just a free body diagram, add them up, friction. It'd be a hard one. Might be the hardest one on the test, but still doable. So, all right. Hope that helps anyone. Take care.